Okay, welcome everyone. I'm going to try something new today. I'm going to go through the study guide for Chapter 7, which is about energy, on this recorder. We'll see how it works. I don't know. Maybe it will help you. Hopefully it will. We'll see. But I'm going to work through the problems kind of quickly. I'm not really going to focus on the teaching every detail because I feel like by the time we get to the study guide, we should know it. But just one extra resource for you to use if you ever don't know how to do a problem or would like to review right before the test. I think this might be helpful. So anyway, let's get started. With the vocabulary, I think you can get these from the vocabulary list, so I'm not going to spend much time on them. Let's just jump right down to the equations that you need in this chapter. We've used quite a few of them. One of them was work is equal to a force times a distance. The second one we learned, potential energy is equal to mgh. That's the object's mass times acceleration due to gravity times height. Kinetic energy is equal to 1/2 mv squared. And then finally we learned mechanical energy is equal to potential energy plus kinetic energy. And so those were the four equations we used throughout most of the chapter. Now let's go down to question number 1. It says, give the unit of measurement for each of the following. Energy is always measured in joules, capital J. Velocity is measured in meters per second. Mass is kilograms. Acceleration due to gravity, it's acceleration, so it's meters per second squared. Height is measured in meters. Work is the energy value, so it's joules again. And force is always measured in newtons. Okay, number 2. What two things must be present for work to be done on an object? Well, work is equal to a force times a distance. So the two things that must be present is a force and a distance. Okay, number 3. A crane is lifting a car into a truck bed. A, is work being done on the car? So is there a force being put on the car, and is the car moving a distance? And the answer is yes. The crane would have to put a force on it and it moved the car a certain distance. Explain your answer. So there is a force and a distance. Okay, number 4 says, that same truck is now traveling with the car on its bed. Is work being done on the car? Now, if we think about the car in this situation, is a force being put on the car? Well, I guess maybe you could say that the truck is putting a normal force on the car, but it's not really moving it in the same direction as the force. And as we've learned about work, that force has to be in the same direction as its movement. So I would say no on this one and put the force is not in the same direction as its movement. Okay, and so hopefully that helps you through page 1. Let's go to page 2 now. Starting with number 5, it says a dog pulls a 40-kilogram wagon with a force of 300 newtons over a distance of 50 meters. How much work is done by the dog? So we're calculating work again. Work is equal to a force times a distance. The force that the dog pulled it with was 300 newtons, so 300 times the distance of 50 meters. Okay, so 300 times 50 would be your answer. So 15,000. 15,000. And the units here you could either put Newton meters or a joule. So 15,000 joules of energy was done by that dog. Okay, number 6, it says how much work is done by pushing a 100 kilogram box 5 meters across the floor by a 20 Newton force. Okay, So again, we're calculating work, and that's equal to a force times a distance. The force is 20 newtons. So substitute 20 in for the force, and the distance was 5 meters. And that will be equal to 100 joules. Okay. Number 7 says a 120 newton sled and rider is pulled by a 200 newton force for 100 meters. The force, though, acts at an angle 60 degrees with the ground. How much work is done by the applied force? Now this goes back to when we talked about work, we found that the force has to be in the same direction as its motion. So if it's at an angle, we're going to have to use our trig functions a little bit. So let's go through and label what we know. Okay, it's pulled by a 200 newton force. So I'm going to label that 200 newtons along this rope. Okay, it's pulled for 100 meters, so the distance is 100 meters. But it acts at this angle 60 degrees. So if we continue our triangle here, let me draw it in. This would be a right triangle. I'm going to call this Fx because that's the component of the force that's in the x-axis, so Fx. And I'm going to call this one Fy. And if we look, it's moving along the ground, so the force that is parallel to the ground, or in the same direction as its motion, is this force. So Fx is really what I need to find. And if you go back to the trig functions, we're going to use cosine of 60 is equal to adjacent, which is Fx, over the hypotenuse, which is 200. We're going to times both sides by 200. And so 200 times the cosine of 60, cosine of 60 is 1/2. So 200 times 1/2 is 100. So that will be a 100 Newton force, Fx. So the work is equal to a force times distance, so 100 times 100 meters is equal to 10,000 joules. And that's how I would work a problem like that. Number 8 is kind of the same situation where we have the force acting at an angle. Let's read it. It says a 175 kilogram bobsled is stopped by a force applied with an angle of 20 degrees with the ground. The sled is stopped in 25 meters with 800 joules of work. What is the magnitude of the force? So this time it's giving us the work, and it's asking us for the force that is required to stop that bobsled. So let's go through and label what we know. So the sled must have been moving, and then this force right here was stopping it. So let's say it's moving for 25 meters. Okay, the force, I'm going to make my triangle here and call this one Fx, this one Fy, and this one is called the force. And so let's write down our equation for work. Work is equal to a force times a distance. We have the distance as 25 meters. We have the work, which was 800 joules of work. And now we're looking for that force, but remember this force has to be in the same direction as its motion, so I'm going to call it Fx, because that's the one that's parallel to its motion. Okay? So let's solve for Fx. If we divide both sides of this equation by 25, so 800 divided by 25 will give me 32. So Fx is equal to 32. So that's equal to 32. What we're really trying to find, though, is this force that was used to stop it. So let's go back to our trig functions and use them to solve for our force. It looks like we have an adjacent angle, and hypotenuse is what we're looking for. So we're going to use cosine again. So cosine of 20 is equal to adjacent, which is 32, divided by the hypotenuse, which I'm calling the force. Okay, I'm going to times both sides of this by the force. On this side it cancels out. And then I'm going to divide both sides by cosine of 20. So we get that 32 divided by the cosine of 20 will be equal to the force. So cosine of, 32 divided by cosine of 20. My calculator is telling me that that force would have been equal to 34.1 newtons. Okay, so hopefully that makes sense, how to do problem number 8. Let's go to problem number 9. Okay, number 9 says, you are loading a refrigerator into the back of a truck bed. Your friend says you can reduce the amount of work by using a ramp and pushing the fridge up the ramp into the truck bed. The ramp is 5 meters long and the truck bed is 1.2 meters high. To push the 400 kilogram fridge up the ramp, it takes 700 newtons of force, and you push it parallel to the ground. Okay, on A it's wanting us to draw the free body diagram for this situation. So let's do that. Here's our ramp. It said the ramp was 5 meters long and only 1.2 meters high. So this is obviously not to scale, but 1.2 meters high would be right here, and this would be where the back of the truck bed is. So I won't draw the truck just for sake of saving space, but this would be the truck bed, the bed of the truck. Okay. We've got this refrigerator here, and you are standing here pushing it parallel to the ground. Okay. And so let's go through and find we're going to have to find this angle of this ramp. So let's go ahead and do that. If I have an opposite and hypotenuse, I'm going to use sine. I'm going to call this angle theta. So sine of theta is equal to opposite, which is 1.2, divided by the hypotenuse, which is 5. And I'm solving for theta, so I want to get rid of sine on this side. I have to use the inverse sine function. So theta is equal to the inverse sine of 1.2 over 5. So let me do that in my calculator. And I'm finding that theta is equal to 13.9 degrees. So this will be 13.9 degree ramp. Okay. Let's go to B now. We're gonna work on our free body diagram a little bit more. But let's go to B and figure out what it's asking us. It says calculate the work done by pushing the ramp or pushing the fridge up the ramp. The problem here, and what makes this problem complicated, is that he is pushing parallel to the ground, but the fridge is moving up the ramp. And we know that with work, the force has to be in the same direction as its motion. So what I need to do is figure out how to calculate the angle here and I'm going to draw in a little triangle, and if this angle is 13.9, this angle right here, 13.9, will be that angle right there. Okay, now let's go and read the question again and fill in everything that we know. This is a 400 kilogram fridge. It takes 700 newtons of force to push it, so 700 would go where your arms are, and that will be the hypotenuse of that triangle. And now we can calculate the work. So work is equal to a force times a distance. We know the distance of that ramp is 5 meters. But we really need to calculate Fx because Fx is parallel to the ramp or in the same direction that it's moving. So let's go through and use our trig knowledge of trig and solve for that. We know that we redraw this triangle down here. Okay. And so this will be your 700 newtons of force that you're pushing the fridge with. But we really want to find Fx. And we know that this angle is 13.9. So let's go through and solve it. We have an adjacent and hypotenuse, so we're going to use cosine of 13.9 is equal to the adjacent, which is Fx, divided by the hypotenuse, 700. We're going to solve for Fx, so we need to times both sides by 700. So 700 times the cosine of 13.9 will give me my answer. And Fx is equal to 679.5 newtons. Okay, so we can substitute this in for our force, 679.5, times that by 5, because he pushed it for 5 meters, and the work that he is going to do on that refrigerator is 3,397.5 joules of work by pushing it up the ramp. So hopefully that kind of makes sense what we did there. Now let's go to part C of this question. It says, how much work would it take to lift the refrigerator off the ground and put it into the truck without the ramp? Was your friend right? And did the ramp reduce the amount of work needed to get the fridge into the truck? Okay, so now you just want to pick it up directly without using a ramp. Let's figure out how much force would be required. This is a 400 kilogram fridge. So we know that the force of gravity on this is mg. So if we take 400, which is its mass, times it by 9.8, so 400 times 9.8, that is equal to 3,920 newtons. That's the weight of that fridge. So in order to lift it, you're going to have to put a net force on it. Your applied force by lifting, so this force here, is going to have to be at least 3,920. Anything greater than that and you'll be able to lift it. So let's just use that as your force. So work is equal to a force times distance. The force that you will have to use is anything greater than 3,920. And the distance you will have to lift it, because the truck bed is 1.2 meters, you'll have to lift it at least 1.2 meters. And so let's take that and times it by 1.2. And I get 4,704 joules of work. This is how much work you will have to put into it to lift it into the back of the truck directly without using the ramp. And so it says, was your friend right? If we look back up here, the ramp, it only took 3,300, 3,400 about joules, and lifting it directly, 4,700 joules. So yes, your friend was right. Yes, he or she was right. The ramp did, in fact, reduce the amount of work that you need. And that's why people use ramp. They offer a mechanical advantage if a ramp is available. So hopefully that question number 9 makes sense to you now. Let's go on to question number 10. And it says, write the formula for finding kinetic energy. Well, kinetic energy is equal to 1/2 the mass of the object times the velocity of the object squared. So always remember to square the velocity. A lot of students will forget that square right there. Okay, let's do problem number 11. It says a cheetah can run with a speed of 31 meters per second. If its mass is 47 kgs, what is its kinetic energy? So we're solving for kinetic energy. Let's write down the equation. It's equal to 1/2 mv squared. Now let's just plug in our values. 1/2 times the mass of the of the cheetah is 47 kilograms. I'm not writing the units in. I probably should, but just for the sake of space, I'm not going to write the units in. We've worked a lot with the units in class, so this study guide, I'm just going to omit them. And velocity goes here. So the velocity of that cheetah was 31 meters per second, and you got to square it. So let's put that in our calculator. 1/2 of 47 times 31 squared. And I'm getting that it is 22,583.5. And it's energy, so our units are going to be in joules. That's how much kinetic energy that cheetah will have at that point. Okay, so hopefully that helps. Let's go to page 3 and start on number 12 of the study guide. Number 12 says, how fast must a 0.005 kilogram bullet travel if it is to have the same kinetic energy as a 20,000 kilogram locomotive traveling at 2 meters per second? Okay, so this is a kinetic energy problem. What I would recommend with this one is solving for the kinetic energy of the locomotive first. Okay, we know its mass and we know it's traveling at 2 meters per second. So let's write the kinetic energy equation up top is equal to 1/2 mv squared. I'm just going to plug in my numbers to that for the locomotive first. So the kinetic energy of the locomotive is equal to 1/2. The mass was 20,000. And the velocity of that locomotive was 2, but we got to square it. So let's put that in the calculator. And I'm finding that its kinetic energy was equal to 40,000 joules. Okay, now if the bullet is going to have the same kinetic energy as the locomotive, we want to know how fast the bullet must be going. So if this is its kinetic energy, we're just going to set that as its kinetic energy is equal to 1/2. The mass of the bullet was 0.005. And we don't know its velocity. We're trying to solve for it. So I'm going to call it v squared. To solve for this v squared, what I would do first is times both sides by 2. So we get, well, okay, let's make it simple. Let's take half of 0.005 divided by 2 is equal to, okay, so 40,000 is equal to 0.0025 v squared. Okay. And now we're going to divide both sides by 0.0025. So 40,000 divided by 0.0025. Okay, that's a really big number. 16 million. So I'm going to move up here because there's more space. So 16 million is equal to v squared. Now, to solve for the v, I need to get rid of that square. We take the square root of it. We take the square root of that side. We've got to take the square root of both sides. So let's do the square root of 16 million. And I'm getting that the velocity of that bullet would have to be going 4,000 meters per second in order to have the same kinetic energy as that locomotive, which is pretty remarkable. I mean, the bullet would have to be going so much faster than the locomotive because its mass is dramatically less. So hopefully that kind of makes sense. Number 13. It says a rolling ball has 300 joules of kinetic energy and is rolling 15 meters per second. Find the ball's mass. So now we're going to find the ball's mass using that kinetic energy equation. Let's just write it down again. Kinetic energy is equal to 1/2 mv squared. Now let's plug in what we know. It says it has 300 joules of kinetic energy, so 300 is going to be what I plug in for kinetic energy. So that is equal to 1/2. We don't know the ball's mass, so I'm going to keep it m. And we know that it's rolling at 15 meters per second, but we got to square that. So now let's just solve this equation. What I would do is times it by 2 to get rid of the 2 there. And so 600 is equal to m times 15 squared. Let's do 15 squared. We'll figure out what that is. It's 225. So 600 is equal to m times 600, or times 200, sorry. M times 225. Okay, now I want to get m by itself. I'm going to have to divide by 225 on both sides. So m, in this case, was equal to 600 divided by 225. We would figure that the mass of that ball is equal to 2.67, and the units for mass are kilogram. So that ball must have had the mass of 2.67 kilograms. Okay, number 14. How fast is a ball moving if it contains 120 joules of kinetic energy and has the mass of 5 kgs? So again, it's a kinetic energy problem. Kinetic energy is equal to 1/2 mv squared. Now let's plug in what we know. It contains 120 joules of kinetic energy, so 120 goes in for kinetic energy, is equal to 1/2. We know that its mass was 5, so I'm going to plug that in for the m, but we don't know is its velocity. So what I would do is times both sides by 2 to get rid of the 1/2. So the 2's are canceled. So that would be 240 is equal to 5v squared. Now I would divide each side by 5. And so 240 divided by 5 is equal to 48 is equal to v squared. Now to get rid of the square, I'm going to square root both sides. So v is equal to the square root of 48, which is 6.93, and the units for velocity are meters per second. So that ball must have been moving 6.93 meters per second. Okay, let's go to 15. It says write the formula for finding potential energy. And it means gravitational potential energy, so potential energy is equal to mgh. Mass times acceleration due to gravity times the height. And we're going to use this equation for the next few problems. So let's go to 16. It says a 747 kilogram elevator raises straight up 164 meters. What is the change in potential energy of the elevator relative to the ground? Okay, well, let's find its potential energy at the top. The mass was 747 kilograms. G is always 9.8 on Earth. The acceleration due to gravity is 9.8. And the height was 164 meters. So let's times that through. 747 times 9.8 times 164. Okay, and I'm getting a very large number. 1,200,578 joules of potential energy is what that elevator would have at the top. So what is the change in potential energy relative to the ground? On the ground, its height is going to be 0, and so its potential energy on the ground would be equal to 0, because 0 times anything is 0. And so the change in potential energy is 1,200,578 joules. Okay, let's go to 17. A high jumper has the mass of 85 kilograms and a potential energy of 1970 joules. How high does he jump? So now we're trying to figure out how high he jumps. Let's go back to this potential energy is equal to mgh. Okay, let's plug in what we know. We know that the potential energy was 1970, so 1970 is going to go in for potential energy. The mass of the high jumper was 85 kilograms. G, we always know G is 9.8, but we don't know height. So I'm just going to call that H. So what I would do is divide both sides by 85 and 9.8. So height is going to be equal to 1970 divided by 85 and 9.8 times by 9.8. So 1970 divided by 85, and then let's divide that by 9.8. And so its height, h, would be equal to 2.36. 2.36. And height is always measured in meters. So we'll put the units down. So that's how high that high jumper would have been able to jump, 2.36 meters. Okay, let's go to 18. 18 says, a car coasts 62.2 meters along a hill that makes a 28.3 degree angle with the ground. If the car's mass is 1,234 kilograms, then what is the change in potential energy? Okay, so what we really need to figure out is how high this car will coast. So we need to figure out its height on this triangle. And sorry, that doesn't look like a very vertical line, but that is a right angle there. So, so let's write down what we know. Potential energy is equal to mgh. So once we figure out the height of this triangle, we can plug it in for the height there, and then we'll know everything that we need to know for this problem. So let's use our trig functions to solve for that. Looks like we have an opposite angle and a hypotenuse, or an opposite side and a hypotenuse. So we're going to use sine. So sine of 28.3 is equal to opposite, which is h, over the hypotenuse, which is 62.2. Now if I'm going to solve for h, I'm going to times both sides by 62.2. Cancels out on that side, so 62.2 times the sine of 28.3. And I'm finding that the height is equal to 29.5 meters. And now we can go back to our potential energy and figure this, how much potential energy he will have. So the mass of the car was 1,234. G is always 9.8 on Earth, and the height we just saw for was 29.5. So let's use our calculator, times that through. My calculator is telling me that it's 300, so potential energy is equal to 356,749 joules is what he will have as he reaches that height. Now, of course, on the ground, his potential energy would be 0, so that is his change in potential energy. And hopefully that makes sense. Okay, let's go to 19. It says a mountain climber scales a cliff that makes a 10-degree angle with the vertical. The climber climbs 231 meters up along the cliff. What is the change in potential energy relative to the ground of a 232.2 Newton mountain climber? Okay, so it kind of has the diagram already drawn on our paper. So this is the cliff. Okay, this is the cliff. I'll draw a little bit of a jagged edge here to designate that being the cliff. It forms a 10-degree angle vertically. What we really need to find right here is this height from the ground. And so we're going to use our trig and see if we can't solve for the height of that cliff. Okay, and our right angle would be right here because that one's the vertical. So let's use our trig functions. What could we do? Looks like we have an adjacent and we have the hypotenuse. So we're going to do cosine of 10 degrees is equal to the adjacent, which is the height, divided by the hypotenuse, which is 231. Let's times both sides by 231. And we find that it's 231 times the cosine of 10 will give us the height. So height here is equal to 227.5 meters. Okay. So when we're doing our potential energy is equal to mgh, we have height, we have g. One thing that we don't have yet is the mountain climber's mass. It told us that the weight of the mountain climber was 823.2. And so if you remember, if this is the mountain climber, weight is equal to mg, and his weight is 823.2 newtons already. We can figure out his mass by using this equation here. It already gave us the weight of the mountain climber. Now we just need to solve for his mass. And how do we do that? Divide both sides by 9.8. So 823.2 divided by 9.8, and his mass is equal to 84 kilograms. So now we can solve for his potential energy. 84 is his mass, 9.8 is his acceleration due to gravity, and the height of that cliff we solved for it was 227.5 meters. Okay. Now let's use our calculator and times that through. So 84 times 9.8 times 227.5. I'm getting that the potential energy at the top of that cliff will be equal to, let's see, 187,278 joules. And of course on the ground his potential energy would have been 0. So that is his change in potential energy relative to the ground. Alright, let's go to 20. Mechanical energy is equal to blank times, or blank plus blank, and that is potential energy plus kinetic energy. So that's the answer for 20. Let's go to 21. It says a roller coaster with a mass of 1,200 kilograms is moving 5 meters per second at the top of a 70-meter hill. What is the mechanical energy of the roller coaster? I always like to draw a picture of what's going on here. So this is a roller coaster, and so let me draw a hill. It says it was at the top of the hill. So here's our roller coaster. Its velocity was 5 meters per second. The hill was 70 meters high, and its mass was 1,200 kilograms. So let's write, it wants mechanical energy, so let's rewrite that. Mechanical energy is equal to potential energy plus kinetic energy. So let's figure out its potential energy first. I think that's always the easiest place to start. Potential energy is mgh, so it's mass. It's 1,200. G is 9.8, and the height of that hill was 70 meters. Okay, that will give us its potential energy, but we need to add in its kinetic energy as well because it was moving. So let's do that. Kinetic energy is 1/2 the mass, 1,200, times its velocity squared. And so let's figure out what those are. So 1,200 times 9.8 times 70. And I'm getting that its potential energy, let's see, 823,200. We're going to add that to its kinetic energy. So let's put its kinetic energy there. So half of 1,200 times 5 squared is 15,000. So let's add 15,000 to the potential energy of 823,200. And I'm getting that its mechanical energy will be 838,200 joules. And that's its mechanical energy. Let's go to number 22. It says a wakeboarder with a mass of 50 kilograms jumps the wake of a boat and reaches a height of 2.5 meters. His velocity is 15 meters per second. What is the mechanical energy of the wakeboarder? So again, we need mechanical energy, which is equal to potential energy plus kinetic energy. Let's go ahead and find his potential energy first. That's mgh. So the mass of the wakeboarder was 50 kilograms. G is 9.8. And the height that he reached on his jump was 2.5 meters. Okay, we're going to figure that out, and then we're going to add that to its kinetic, which is 1/2 the mass, times the velocity. His velocity was 15 meters per second, so 15 squared. So let's figure out his potential first. Finding that his potential energy was 1,225 joules. We're going to add that to his kinetic. (5,625 joules). So let's add those two together. And we get 6,850 joules of energy. That's how much mechanical energy that wakeboarder would have. Let's go to 23. It says an F-16 fighter jet with a mass of 12,000 kilograms is traveling 600 meters per second at a height of 4,000 meters. What is its mechanical energy? Now, obviously, the energy of this fighter jet is going to be an extremely large value. Let's figure it out. So mechanical energy is equal to potential energy plus kinetic energy. Let's do potential right here. So its potential is mgh, so its mass is 12,000. G is 9.8. And its height was 4,000 meters. Okay. Once we figure that out, we're going to add it to its kinetic, which is 1/2 the mass, is 12,000, times its velocity was 600 meters per second, but we got to square it. Okay, so let's figure out his potential energy first. And it's such a large number, I'm going to put it in scientific notation just to kind of shorten it a bit. 4.704 times 10 to the 8th. And we've got to add that to his kinetic energy. Which is 2.16 times 10 to the 9th joules. And so when we add them together, I'm getting that the mechanical energy of that F-16 fighter jet would be 2.63 times 10 to the 9th joules. And so, as we predicted, that fighter jet has a lot of energy, a lot of mechanical energy. And so you can write it in standard form if you like to. It's just a lot of zeros to keep track of and a lot of placeholders to keep track of. So when numbers get really large or really small, I like to switch to scientific notation. So hopefully that makes sense. Okay, we got one more page on the study guide. Let's get to it on page 4. Let's start with 24. It says, explain the law of conservation of energy. Let me just explain it instead of write it out to save time. But the law of conservation of energy says that energy cannot be created nor destroyed, but it can be converted from one form to another. And we're going to see that in the next few problems. where potential energy can be converted to kinetic, and kinetic can be then converted back to potential. And so let's get started on 25. It says that a ball has 17 joules of kinetic energy and its mechanical energy is 25 joules. It says on A, find the potential energy of the ball. Well, this goes back to mechanical energy is equal, so the mechanical energy is equal to potential energy plus kinetic energy. Now let's just plug in what we know. Mechanical energy is 25 is equal, we don't know potential energy, but we do know that it has 17 joules of kinetic energy. So now we have a simple equation. We subtract 17 on both sides, so minus 17 on both sides. Minus 17. So 25 minus 17 will give us our answer, and that is 8 joules. So the potential energy would have had to have been 8 joules. So that's our answer for A. On B, it says, if the ball has a mass of 3.2 kilograms, what is its height above the ground? Okay, whenever we see height, we should think about potential energy. So potential energy is equal to mgh. And we know that the ball had the potential energy of 8 joules, so let's plug that in. 8 is equal, the mass is 3.2, g is always 9.8 on Earth, and the height we don't know, but we can solve for it. And so if you solve for it, you should get, I would do 3.2 times 9.8, and that will be 31.36 times h. Now let's divide each side by 31.36. And so the height will be 8 divided by 31.36. And so the height is 0.26 meters. Okay. And then on part C it says, what is the speed of the ball? When it says speed, you should think of kinetic energy, which is equal to 1/2 mv squared. Now let's plug in these values. And I'm going to work it down here. So 1/2, the mass of the ball was 3.2, and the velocity we don't know. That's what we're trying to solve for. But we do know that it's kinetic energy. It told us in the problem that kinetic energy was 17. So let's take half of 3.2. So 17 is equal to 1.6 v squared. Let's divide both sides by 1.6. So 17 divided by 1.6 is 10.625 is equal to v squared. Now to get rid of that square, we're going to square root both sides. So the answer, the velocity of that ball, will be the square root of 10.625. And I'm getting that the velocity of that ball is 3.26, and the units are meters per second. Okay, so hopefully that makes sense on 25. Let's go to 26. 26 is going to take some time, so let's read through it. A 5-kilogram ball is swinging back and forth on a string as shown below. You may make the following assumptions. A is its highest point. The speed of the ball is 4.3 meters per second at point B, and the ball is 23 centimeters above the ground at point C. So we've got its mass. I'm just going to underline some important things. We've got its mass. We've got its velocity at point B, and we know its height above the ground at point C. But this centimeters, we're going to have to switch that to meters, and that is 0.23 meters. So 0.23 meters. Let's not forget that. In fact, I'm going to put that in right here at point C. That is 0.23 meters. B, its velocity, it's 4.3. And A is its highest point. So at its highest point, its velocity is 0. Okay, now let's fill in the chart. It wants us to come up with all of these numbers. And I always think that maybe the easiest place to start is at the very bottom of the pendulum, because we know at the very bottom of the pendulum its height is 0, so it's at point B, its potential energy is going to be 0, and that is because its height was 0. Anything times 0 is 0, so that's an easy place to start. Now let's figure out its kinetic energy at point B. So kinetic energy is equal to 1/2 mv squared. So 1/2, the mass of this ball was 5 kilograms, and we know at point B it was moving 4.3 meters per second. We've got to square that. So let's do that. And I'm finding that its kinetic energy at point B was 46.23 joules. This will be in joules, this will be, all of these will be in joules. Velocity is meters per second, and height is in meters. So, okay, now in point B, if we remember, mechanical energy is equal to potential energy plus kinetic energy. And so if we take these two and add them together, it tells us what the mechanical energy. So we've already figured out its mechanical energy. And part of the key to this problem is realizing that mechanical energy for this ball is not going to change from point A to point B to point C. It is always going to be the same. And that is because of the law of conservation of energy. It can never have more or less energy than it does at a single point on its travels here. So we're just going to go ahead and fill in the mechanical energy at point A and point C have to equal 46.23. Okay. Now, you can pick whether to solve for A or C. Let's go to A. I think maybe A might be a little bit easier. If its velocity is 0 at point A, because it's at its highest point, so velocity is 0, we know that its kinetic energy is going to be equal to 0 as well, because it doesn't have any velocity. If we know its mechanical energy is 46.23, its potential energy has got to be equal to 46.23 as well, and that's because kinetic and potential have got to add up to mechanical. And so we can easily use this equation right here to solve for potential energy. And if we know its potential energy, we can solve for its height at point A. Let's do that over here. Potential energy is equal to mgh. The mass of this ball was 5. G is 9.8. We don't know the height, but we know that its potential energy was 46.23. Okay. So I'm going to solve for height. And I'm finding that the height is equal to 0.94 meters. So 0.94 will go in the height box at A. So we know that this would have been 0.94 meters. Now we can go to part C. Part C is a little bit difficult because it has some height, but it's also moving. It's not as high as A, so we know it's got some velocity and height, which tells us that it's going to have potential and kinetic energy. The easiest place to start, and really the only place you can start with part C, is to solve for its potential energy. So let's solve for its potential energy at point C. We know that its mass is 5, G is 9.8, and we know its height is 0.23 meters. So let's times that through. 5 times 9.8 times 0.23 is equal to 11.27. So I'm going to fill that in. 11.27 is its potential energy at point C. Now we can use this equation to help us figure out what its kinetic energy will be. So what I'm going to do is take 46.23 and subtract 11.27, and that is 34.96. And so we can figure out what kinetic energy is that way. Now we know what kinetic energy is, we can solve for its velocity. I'm running out of space here, so I'm going to do it up here. If we know its kinetic energy is 34.96, that is equal to 1/2 its mass times its velocity squared. And so we can solve for v in this equation. So 34.96, I'm going to times it by 2 and divide it by 5, and that is 13.984 is equal to v squared. And then we'll take the square root of both sides. So the velocity at point C will equal the square root of 13.984. And its velocity at point C will be 3.74 meters per second. So hopefully that makes sense. A is its highest point, so its velocity is 0. As it swings down to B at its lowest point, its velocity was 4.3. And as it swings back up, it's going to lose a little bit of speed, and so it went down to 3.74. So hopefully that makes sense. Let's go to the last problem, last set of questions here. Number 27. It says a roller coaster of 500 kilograms is to travel from 8 meters per second down a wavy hill. It will coast without friction. Near the end of the ride, it will make a death-defying jump. Okay, so there's really no question on 27, so let's go to the next one, which says 38, but it should say 28, or 27 really, but anyway, let's solve this set of questions here. We know that its mass was 500 kilograms, so I'm going to write that in. It's starting at 8 meters per second, which is already given on our diagram. And it's going to coast without friction down this track. On 38 it says, what is the total energy of the system at the top of the hill? Total energy is mechanical energy. And that's equal to potential energy plus kinetic energy. So we've got to figure out what its potential energy would be. We have its height of 80 meters. So let's, the mass is 500 kilograms times 9.8 times height of 80. And we're going to add that to its kinetic energy, so 1/2 the mass is 500. And its velocity it was moving at initially was 8 meters per second, but we got to square that. So let's times that through. So I'm getting that the potential energy was 392,000. Let's add that to its kinetic. Of 16,000. And so its total energy would be 408,000 joules. And so that's its mechanical energy at the top of the hill. On 39 it says, what is the total energy of the system at the bottom of the hill? And this is a good question because its total energy is not going to change throughout its path on this track. it's simply going to convert potential energy to kinetic energy. And so at the bottom of the hill, it's still going to have 408,000 joules of total energy. Okay, let's go to number 40. It says, what is the speed of the car at a height of 30 meters? And it didn't really tell us on the track where 30 meters was, but we don't really need to know that. We have its mechanical energy. We could figure out what its potential energy is at 30 meters, and then from that we could figure out its kinetic energy to figure out the velocity. And so that's our kind of our path that we're going to take to figure out this one. So let's figure out its potential energy at 30 meters. I'm going to do it up here. Potential energy at 30 meters is equal to its mass, which was 500, times 9.8 times 30. And that is equal to 147,000 joules. And if that's its potential energy at 30 meters, we know its total energy was 408,000, so we can take 408,000 and subtract 147,000. And that tells me that its kinetic energy at 30 meters would have to be equal to 261,000 joules. And that is equal to 1/2, its mass is 500, times its velocity squared. And so we can take half of 500, which is 250. Let's divide 250 on each side. So 261,000 divided by 250, which is equal to 1,044, is equal to v squared. Take the square root of both sides. And its velocity at 30 meters would have been 32.3 meters per second. Okay, two more problems. Number 41, it says, what is the speed of the car at the bottom of the hill? At the very bottom of the hill, it's right here, has a height of 0. So it has no potential energy. We can use that to figure that it's all going to be kinetic energy. And so all of its energy, which was 408,000, is going to be its kinetic energy. So we're going to set that equal to 1/2 the mass times the velocity squared. Okay, again, half of 500 is 250. So if we take 408,000 divided by 250, that gives me 1,632 is equal to v squared. Take the square root of 1,632. Let's take the square root of both sides here. So the velocity is equal to 40.4 meters per second. That will be its max speed because that's at the bottom of the hill. So it will never go faster than 40.4 meters per second. Okay, last problem. It says, what is the speed of the car after landing on the 15-meter hill? So it's going to jump right here and then it's going to land on this hill that is 15 meters high. Let's find the potential energy here at 15 meters. So the potential energy at 15 meters is equal to its mass, which is 500, times g, which is 9.8, times its height of 15. So let's times that through. And I'm getting that is 73,500 joules. Okay, and if it has that much potential energy, the rest of it must be kinetic energy. So I'm going to take 408,000, subtract 73,500, and that will tell me it's kinetic energy. So let's do that. And I'm getting that the kinetic energy was 334,500, and that, we need to find its speed, is equal to 1/2 the mass, it's 500, and the velocity, we don't know, so we'll put it as v. So again, half of 500 is 250, so I'm going to divide 334,500 divided by 250, and that gives me 1,338 is equal to v squared. We take the square root of both sides. And the velocity there will be equal to 36.6 meters per second. And so that's what it will finish, that's what its speed will be as it lands on top of that 15-meter hill. Anyway, hopefully that makes sense. That's the whole study guide for the energy chapter. And hopefully that helps. Thank you.